Solenoid actuators are an essential but often unnoticed technology. They provide fast and precise motion that drives everything from valves, locks, safety mechanisms, you name it. Let's unpack some of the design challenges that an engineer usually faces in a design process of such systems. We'll look into this in detail by leveraging SimScale's cloud-native solution that provides us access to a multiple physics set of simulations. So we are going to look at an electromagnetic simulation, then followed by a thermal analysis, and then of course analyzing the performance of the valve under the expected fluid flow conditions. Hi, my name is Khairi. I am part of the solution engineering team here at SimScale. So the case study that we have here today, let's take a look at first unpacking the CAD assembly that we have. So we have two cross sections here, one of an open valve and a closed valve, but essentially the main components are we have the aluminum housing, we have the solenoid bushing, an excited coil, essentially that generates the energy needed to drive the motion. We have the plunger itself, and of course the valve body. Right, and the objectives of this analysis essentially is decomposed into three main areas, right? So on the electromagnetic side of things, we're interested in investigating the magnetic field buildup in time, the minimal force required to move the plunger, and of course, how quick does the force reach its maximum, right, in a transient sense. Then on the thermal analysis side of things, we need to make sure that this heat that's being generated by the coil is not overheating the system, or maybe we also want to analyze the environment that the solenoid is placed in and just make sure that everything is operating in a thermally optimum manner. And of course, after all of that, we could run lots of different simulations of different valve openings, analyzing different flow rates and just understanding how does the valve perform from two points of view. As one of them is the pressure drop in the system, but also is the fluid flow structure optimal. And what I mean by optimal, like do we have large recirculation areas, etc., etc. Right? So now let's take a look at how everything would look live directly in SimScale through a live demonstration of the platform. Now, all I'm going to be doing here is simply switching between tabs because SimScale is completely cloud native. And from here, I can jump in directly to the SimScale website, and which is usually the space where you start all of your work directly, right? So you go to the SimScale website, you log into your account via username and a password, and from there you jump directly to your dashboard. Now the dashboard essentially is a data management system that allows you to manage all of the simulation work that you have done. I like to make a quick joke usually about this with our clients, is that your IT department is always going to be very happy to be using SimScale because they don't have to worry about storage. There is no license updates. You always have the most region of SimScale deployed live for you at any particular point in time. They don't have to invest in any hardware. There is no hardware setup. You're not tied to a particular computer nor a location. It's very, very flexible on that regard. And the dashboard also gives you some opportunities for collaboration, right? So you have the My Projects area is only the projects that you have worked on, and they could really be kind of anything, right, from all sorts of different physics, but you also have common shared spaces with your colleagues, for example, in a particular team. You might have, let's say, Project A, Project B, Project C, all belonging to one particular folder, which is Customer 1, etc., etc. So it becomes easy to find those projects and just have a nice integrated system to manage all of the data available in the portfolio that's being worked on. Now, let's make a quick dive into SimScale and analyze the simulations we have talked about earlier. And I'll do this by jumping into the SimScale Workbench. The SimScale Workbench that we see in front of us here at the moment is the space where you do all of your simulation work. You start by importing a CAD geometry, and that is basically any CAD geometry that you work with, because we support almost all of them. So whether you're working with SolidWorks, Inventor, Rhino, CATIA, Creo, NX, etc. Right? Of course, you can also bring in the native formats directly into SimScale, like step files and so on. What we're seeing in front of us at the moment in the screen is the complete valve assembly. We can make a section view just to understand what we are working with. And then we're going to be able to break this CAD assembly down into subcomponents that we're going to be using to analyze the different physics, which we'll take a look as well on in a second. Now, you can do this also kind of the dividing of the CAD model into its subcomponents also directly within SimScale, right? So we do provide a CAD editing tool that allows you to do some basic operations like extracting fluid regions, automatic fixing of interfering bodies, and lots of other things that allows you really to prepare the CAD for simulation rather than creating a CAD from scratch. And once you have all of your CAD models prepared, so for example, for my conjugate heat transfer analysis, for my electromagnetics analysis, I can essentially go ahead, create a simulation, and start working. As I've mentioned earlier, SimScale provides you access to a multiple physics platform. So whether you're dealing with the fluid mechanics side of things or the structural mechanics, or of course, electromagnetics as well. We'll start by taking a look at the electromagnetic simulation, right? So SimScale provides you access within its electromagnetic solver to magnetostatics, AC magnetics or time harmonics, electrostatics, and time transient. Of course, with the possibility of adding thermal coupling into the equation as well. Now, jumping to the post-processor of our transient electromagnetic simulation, we see here the complete simulation setup from the materials. We do provide you also with quite a comprehensive material library within our electromagnetic solvers, various different steel grades with their BH curves directly as well imported into the platform, various different magnetic grades as well that we see over here and so on. The excitation for the coil that I have here is around 2 volts and it's a DC excitation. And what we're visualizing at the moment is essentially the magnetic flux density distribution building up during the excitation of the coil, right? Up until it reaches essentially the maximum capacity that this DC excitation is going to be able to provide. Now, we could analyze here also some other fields like the magnetic field intensity, the current density, and so on and so on. Now, in this particular analysis, what I would be interested in looking at a lot is, of course, the amount of forces that are being generated also on my plunger. So we can take a look here at the transient response of the force on the plunger, and we can see the following response. So the force reaches approximately a steady state value at around 2.3 newtons for the last set of operations. And from this, we can deduce the overall response time from the force, and we can then use this force, of course, also to calculate the stroke length that it can generate to control essentially the amount of closing of the valve that we desire. Some other outputs that we can extract from here are also the ohmic losses in the systems. This is going to be important later when we set up our thermal simulation, etc. Right? So that's on the electromagnetic side of things. Now I can go ahead and set up, for example, a conjugate heat transfer problem and continue essentially the analysis based on that. So what we have here again is our materials defined. We're simulating this in an environment of 20 Celsius degrees, and we have essentially our power sources, or basically the components that are generating heat essentially added into the system. And in this case, it is our coil mainly, and we can from this also analyze how much heating overall is happening into the system. So we see, for example, that the coil reaches a temperature of around 45 Celsius degrees, while the aluminum housing essentially of the solenoid valve is still within acceptable temperature, around 30-35 Celsius degrees. Of course, this is a quick entry, let's say early stage simulation. In more detailed stages, one can include much more details into the system and just make a more high fidelity simulation as well. So SimScale should be able to provide you with a complete solution from the early stage to the high fidelity analysis of the tool. Finally, what is also very interesting to look at is, of course, the fluid flow side of things. So for example, here we see the fluid at a particular flow rate. I'm going to talk about that also a little bit later, through the valve body. And we see that this actual design of the valve is actually not really ideal, we are generating a large recirculation area towards the end due to this shooting jet from this side. Actually, this can be also seen quite easily when we look at a cutting plane in the system. We see here essentially our cutting plane, and the vectors indicate really a large recirculation zone happening here. Now, this could be one particular deduction that, for example, this valve body needs to be improved and so on. But what we can also leverage SimScale for is the ability to run multiple different simulations at the same time in parallel. So for example, here for my velocity inlet, I have various different flow rates that I would like to analyze. This, of course, can be applied to any particular physics. So it could be I'm applying different heat sources to my domain, or I'm applying different current or voltage excitations to my coil. And then I can leverage this and run various different simulations at the same time in parallel. So if one simulation takes 5 minutes to finish, all of these simulations are going to take, let's say, 5 minutes to finish. And then in the end, I'm able to extract a nice plot that shows me how does the flow rate that I am supplying changes, essentially, or basically what is the connection between each flow rate and pressure. And I can get some sort of a performance curve out of my analysis. Lastly, it's important to mention that with SimScale, you are also never left alone with the tool. In case you ever require support from us, you can always leverage the support chat in the product. This is a live support with actual simulation experts and SimScale experts. You can just write them anything like, hi, I need help in X and Y, and then you can expect a really quick reply time. The first step of this, you might go through an AI agent, and then once you're connected with our team, essentially you have your live simulation assistant essentially for your help. All right, that's it all for today. Thank you for listening and take care.